And I had some coffee, so I hope I'm a little faster this time. Arno will be very appreciative. So we're going to continue about ICA, which I think is a fundamental tool nowadays for moving from recordings, study of fuzzy scalp patterns, highly fuzzy scalp patterns, to much better defined dynamics and imaging of source-resolved EEG data. So I'm going to recap a little bit to hope it sinks in a little better what the idea of this blind source separation is. What was before blind source separation would be non-blind source separation. So given this problem, signal processing problem, someone would have made a model of a saxophone sound and made a model of the resonances in the man's voice, and then tried to fit it to the data. Sort of projection pursuit was the hot topic in the 80s. And so that's non-blind. But you had to know that there was a man there, and you had to know there was a saxophone. So blind source separation meant let's look for sources of information in the data, irregardless of what they are and what form they are, what form their activities take. If those are added up, and the key factor mathematically was and is that if the PDF, if the probability distribution function of their individual moment contributions to the signal are not Gaussian, then it should be possible to effect the unmixing of those information sources and in changing of coordinates, basically in a mathematical sense, from microphone 1 microphone 2 to source 1 source 2, and thereby doing that arrive at the only two sources of information in the signal. So the same goes for the EEG, that you have different sources acting mainly independently, projecting instantly to the electrodes and summing exactly linearly at the electrodes. So in this sense, the brain problem is actually easier than the acoustic problem. In the acoustic problem, you have finite propagation velocity, right? So that the phase of the received signals at the different recordings, if you have an oscillatory, for instance, can be quite different at the different microphones. It makes the problem more difficult. You have to deconvolve those phase differences. With EEG, the propagation is instantaneous for all reasonable extents and purposes, and therefore, the summation is exactly linear at EEG frequencies. So the problem is actually more ideally suited for ICA. So we're going to talk more about it, and I showed this. Let's go through it with perhaps a few different comments this time. Remember that we decomposed using this would be extended Infomax ICA. We decomposed 100 channels, half-hour data from 100 channels. We got a half hour of 100 independent component processes, and we show a subset of those here for illustration purposes. We got a perfectly formed ECG, which could have perturbations if there were such. It would be sensitive to those. Those aren't averages in any sense. Those are single trial, showing the single trial differences. And its projection to all the electrodes, even though it's very hard to see that in raw data, and certainly no frequency filter or any other simple filter could take that out. And and this was done, ICA doesn't know there is a head. It doesn't know there are electrodes, that there are electrode positions. It doesn't know anything. It's only, it sees each frame of the data as just a statistical collection of numbers, ordered statistical set of numbers, a vector of numbers. And it just takes all those vectors, it shuffles actually the time courses during the decomposition to make it more statistically smooth. And It just sees a pile of maps, basically. You can think of it as it, but it doesn't know there is a head, and that the order of the channels has anything to do with space. All it sees is the set of vectors, and it finds a basis for those in which the differences, the moment-to-moment differences, are as independent of each other as possible. So it can find scalp muscles here, individual scalp muscles. Now, let's talk a little more about this. This is a example where ICA couldn't use one dimension to capture the eye blinks. You see the eye blinks at the top of the slide, very clearly expressed in the frontal EEG channels. It couldn't find one map. Now those two maps are very close to each other. In fact, Julie might have put the same map there by mistake. It should be slightly different. And if you back projected, we multiply those time courses by those maps and made a movie of the result, what you should see is something that accounted for by the fact that when you blink your eyes move up slowly. They move up, and apparently it moved up slowly here because this component is always slightly before that component, but not distinctly. So that means they're not actually temporally independent. The independence that ICA is looking for is instantaneous independence. So delayed dependence can be something somewhat different. But in fact, these are not totally independent, even from the viewpoint of instantaneous dependence. And so Jason Palmer, working with us, gave us the interpretation that what ICA is actually doing is separating the data into mutually independent but dependent subspaces. Okay, so that's an example of a dependent subspace. Those signals are not independent of each other, but do you see any eye blinks in any of the other independent components? Any of the other ICs, we say? Well, you don't. You can't see any eye blinks in the other components. So what IC has done is separated that dependent subspace away from all the other dependent subspaces. And when those dependent subspaces have only one dimension, only one basis element, only one map, only one signal, then you call them an independent component. So the number of independent components in that sense is not necessarily the same as the number of channels when you do this, what's called a complete decomposition. And it means that ICA found, well, the most independent basis possible for those, but it failed to find an independent basis. And examples of that could be activity that was moved around, or in this case, it had some temporal sequence that was slow enough to be captured by EEG. Okay, so that's a deeper look, and there's a function not yet in the menu called that looks for pairwise mutual information and between all the components, and then it tries to block them into dependent subspaces. And it's a very interesting one. I think we should put it into a plugin to raise its visibility, because it's something that's an important question. And we talked about these different rhythms, that oscillatory phenomena that do relate to cognition in some way that's not very clear. One clear interpretation is the association of alpha activity with what's been called idling, or reduction in sensitivity, or reduction in the proclivity to respond to incoming input, which here is coming at appropriate time and place for the experiment. Now, many of you, how many primarily work with ERP measures of EEG? Okay, maybe half. How many work with ERPs and other things, and other measures? Okay, this or something. And how many don't work with ERPs at all? Okay, very few. Okay, so I will talk about ERP analysis. Here's a channel. It looks like PZ for some of you. And now we look at an ERP image and we see, oh, this is what was the experiment? This was it's probably Marissa's experiment where you had a target appeared suddenly on the screen. You're waiting for one of these, you're going to press the button and wow, it appeared. So you get a P300s, quote unquote, better called the late positive complex in the ERP average. So this was from one subject. There were some 400 or 500 trials. But what we show is the time course of potential in each of the trials. But we sorted it by the size, by the positivity in that time window that's indicated there. And I'm sorry, it doesn't have it doesn't have the time markers. But it includes 300 milliseconds, probably. So what do we see? There's a distinct P300. I'm sure it's statistically reliable. But using this analysis, we see right away that in about a fifth of the trials, it isn't there. Even though these are trials that the subject responded to, yes, this is a target. So, if you just look at the average, you don't know anything about that. So what I call this is trial-by-trial analysis. So looking at the differences in the single trials, one can learn a lot more about the relationship between cognition and or experience behavior and the EEG. So if your interpretation is that the P300, quote unquote, is something that occurs, as every time you see a target, it's not true. Although it's associated with the target most of the time, that is true. Now here is a picture that we put into the book on the ERP handbook edited by Steve Luck. And this shows one subject. It may be the same subject. And it shows the trial sorted and sorted in various orders. Well, it's sorted by amplitude again and smoothed less, so you can see more trial-to-trial differences. Vertically smoothed less. And here is one component process that's contributing to that channel, the PZ channel. Here we scale the amplitudes here to their projection to a single channel, to the vertex channel. So this represents real microvolts that project to the vertex channel. Of course, other channels will receive differing amounts of voltage projection from these component processes. So this is a central component process that indeed does have this positive response at 300 or 400 milliseconds. But here are 5 more independent component processes that have sorted the same in the same order, that have quite different projections. And you see that if you sort by the same order, you don't see the same kind of phenomenon trial to trial, the same ratio as trial to trial in these other processes. So they are independent. In the sense that their exact amplitude or particular latency of the exact peak and so on is differs according to the component process. So we call these effective sources. They are all associated, well, except for the IC8 on the left there, which is clearly as the scalp map that would be associated with eye movements, and in fact could be eye movements. I don't actually remember. But these others are clearly can be fit by a single equivalent dipole. That means they can be fit by coherent activity across a single patch of cortex, small patch of cortex. They're completely compatible with effective brain sources. in the sense I talked about. Now, summed together at their projection, they produce this pattern. Is that the whole ERP? No. We again smooth more, you can see this pattern. And what's the difference? So this is the pattern at CZ. This is the pattern produced by these 6 processes in the brain, which are in different locations. You see there's occipital, parietal, central, and frontal. And they're all projecting to CZ. Do they explain all of what's going on at the CZ electrode channel? And the answer is no. If you take the difference of those 2 Earth images, you see this. In some trials, there's still other potentials that play a role, and particularly in the trials in which there's a large late positive complex. So that's why the term complex was originally put in at the same time as P300, and P300 got picked up. But the complex means that there's various things contributing to it. Okay. So now, how much do they contribute? This was a effort by Makoto. I asked Makoto to make. This is a plugin you can use that takes different components from one subject's decomposition and looks how much of the EEG they account for. So in the top box there's a map of power accounted for by variance accounted for in each EEG channel by that component process. And you see the maximal projection is to that right parietal channel, scalp channel, but it only accounts for 30% of its variance. Even though it looks like that component process is aimed right there, that channel picks up 70% of its variance comes from other places. Same for here. This is a tangential, probably mu component, whose dipole location, equivalent dipole location, is about at the hand somatomotor area on the right. Same thing. At max, it contributes to a lot of channels, but at most 30% to them. And here's another 30%er. Now sometimes, of course, so 30% variance is most common, that a scalp channel has contributions from at least 3 or 4, but probably quite a few more sources. And this is even after you take out artifacts, which ICA does very, very good job of by separating them out into separate components. And here's one of those. And because it has to do with the scalp muscle, and the muscle is above the skull, it projects very clearly to the supervening electrodes. And 60 or 70% of the variance of that channel, shown there at the tip of the arrow, is accounted for by this single muscle component. That's why people have always been wary of interpreting data near the temples. And here is even more so. The subject was making lateral saccades, left and right, whose projection of the scalp is shown in component 1 there, map, and its percent projection to the scalp channels go as high as 100%. So if you put electrodes near your eyes, there's almost all the signal comes from eye movements, and that's why they're called EOG electrodes. But not all the signal comes from, right? So you'll see them represented very smoothly and cleanly in other component processes. Now this is not a very good decomposition. This is, when I see things like this in the top components, I think there's a lot of noise left in the data. You need to pre-process the data better and take out, things that will never occur again, which are therefore independent of everything else. So if the subject, for instance, were to go like this, in that 1 second, they would put in hundreds of maps that would never occur in the data again. It would be independent of everything, and ICA would have to say, whoa, what should I give a component to? Excuse my anthropomorphization. So I would tell the student, if this were a student, to try rejecting more messy data, that means non-stereotyped data, and the results would be better. These are not could not be associated with a single patch of cortex with a dipolar projection. Okay, but the overall picture of this plugin, given by this plugin, is that scalp signals are strong mixtures of brain sources. So that's the reason not to go to the source resolved EEG analysis and interpolation. So in a certain sense, things you see at the scalp are epiphenomena because they don't relate to a single brain source, particularly not one directly below the channel, only in some vague part. What's really of interest is what's going on in the cortical networks that we are able to monitor using scalp EEG. Here's time frequency analysis. John hasn't covered time frequency analysis yet, but here is the spectral perturbations that occur, sort of the average spectral response induced by a set of stimuli or a set of events. And here's at the channel, this is probably FC. So there's what happens you get an alpha blocking, 10 hertz blocking following the stimulus, and some other phenomena. Now if you look at what happens in various component processes, there's a frontal at the top, also frontal in the middle, and a occipital process you see quite different things are happening, and they're all contributing. See the white dots in those maps, they're all not green, right? They're not on top of a zero projection. They all get a positive or negative going projection in this sense, although the sign of those projection, of course, changes as the sign of the activity of those components change. But they all get some sizable projection from those component processes. And so therefore, if you look at that means that this ERSP is calculated on a sum of things. And these are the things that, some of the dominant things that processes that they actually sum. Although power is not summed linear, the power of a sum of things is not the same as the sum of the powers of things. Okay, so here's the intertrial coherence, the phase regularity trial to trial that you see at the channel, and here are the phase regularities that you see at the major contributing sources. And you see you can learn a lot more about what's going on in the brain by splitting up the data into these sources. So classifying ICs is something Luca's working on a sophisticated model for, and has actually a very nice website that you can use to practice classifying ICs yourself, or even contribute to his project by, after you've trained, contributing some labels for some ICs. So there's non-brain sources, such as here eye blinks. Subject was eye blinking regularly in the experiment here. Here is a muscle component, and with its characteristic EMG spectrum. The fall off at the top bay there, around 50 hertz, obviously being a filter, some sort of notch filter that was put in the data. Here is clearly a brain source. This is a bilateral. This is again the bilateral occipital. And you see a very strong alpha peak in the spectrum. And very orderly trial-to-trial replicability of the dynamics. So that's a brain component, and this is a frontal midline component. Just look at the sharp peak at theta, around 6 hertz. And again, the regularities in the trials, although you see at any one instant there's not all positivities here, right? There's positivities and negativities. So the phases remains fairly random. So that's why you have only this background alpha ringing as some people in ERP analysis call this. Perhaps the alpha ringing is stronger here. It's not because alpha is stronger, but just because it becomes a little more lined up. There's a little bit of partial phase resetting. It creates the appearance of something getting bigger in the ERP, but it may not be at all. So what kind of things does ICA separate out? Blinks, lateral saccades, lateral eye movements. Again, the eyeball is a dipole, and so when you move, so it's projecting this way, but when you move here, it projects more into these electrodes and less into these, and so on. So, or more positive and more negative, and therefore you get a strong projection to the EG. Here's a postauricular muscle. I think it's placed too high on the head. This was our first try at co-locating heads and electrodes. And you see the subject was tensing that muscle for the first 200 seconds or 200 trials. Then it went quiescent for 100 trials, and then for 50 trials it was active again, and then it went quiescent. Usually subjects are not aware of this, and that wouldn't be true of all the other muscles that were being recorded, this high density. So there's a lot of information about subject cognition in these muscle signals. I haven't had anyone say, oh, I'm going to study it, but here is ECG and its characteristic pattern of contamination. Now, as I said, you can separate out several muscles. So this is from one data set, several muscles. And from the, these are 256 channel recordings. And so you can see the polarity reversal is characteristic. The polarity reversal occurs at the end of the muscle, at the insertion of the muscle into the tendon. And by looking Gray's Anatomy here, you can see which muscles these are. Again, no one has done a dissertation to prove that. And even the muscle people say, well, you know, putting needles into deep neck electrodes is a little dangerous. So, Klaus Grauman has a project to take good fMRI and to really make the connections. And here's the EMG spectrum of all these. Now, ignoring, not necessarily rejecting, but ignoring those components, let's look at the other kinds of component processes that ICA separates the same data set into. And what we find is these undeniably brain processes. Why? Because a single equivalent dipole model, even in a template head model here, fits the scalp map associated with that component to within 2% residual variance across 256 channels. So ICA has done an extraordinary job here of finding a source that is completely compatible with the origin in a patch of synchronous activity within a small patch of cortex, located, for which the equivalent dipole is sort of located in the electrical center of gravity, so to speak. Sometimes you find bilateral components, and we've used this one a lot in these slides. It's not found in every experiment or in everyone. And here, again, it can be accounted for almost perfectly, 1% residual variance with a two-dipole model. The dipoles located bilaterally, as if they might be connected by parallel visual projections or by bidirectional corpus callosum. And then, so you can monitor now a whole variety of specific cortical processes and their differences in trial to trial. So you can look at network dynamics. Here was an early example of two processes from one data set, left and right. Very similar spectra, very similar opposite scalp maps, same spectral peaks, and related ERPs representing, again, this partial phase coherence at alpha plus some slow waves. But ICA said that these are actually independent of each other. They're never synchronously active, or statistically they're not at all. And these are very specific contributions to scalp alpha. See, they project to the whole posterior channels, central posterior channels, and the one on the right projects as well to the frontal channels, central and left. So ICA, now this is a little bit of visual math. What does ICA do? It takes the scalp data matrix, EEG.data in our case. It finds a matrix, W, or the unmixing matrix, a square matrix, that spatially filters the data, transposes it from scalp channel by scalp channel into component process by component process, such that the activations of those processes resulting from that multiplication are as independent of each other as possible. Now, if you multiply that by a matrix that's obtained simply by inverting the unmixing matrix, you get the mixing matrix, and whose columns are these scalp maps. The columns of the mixing matrix show how each of those time courses project to all the channels simultaneously, and then the channels sum all those time courses. So when you do this multiplication, you get back exactly the original data. So ICA doesn't lose anything. It separates the data into two parts: time courses and scalp maps. But it doesn't lose scale. It does, so for instance, where is the scale located? In ICA, we typically, by convention, make these more or less RMS root mean square 1, so that the scale amplitude is contained in the scalp maps. But you could do the opposite, and it doesn't matter. And the same for the projection for the polarity. As we show the maps here for convenience in a single polarity, but when it's multiplied, for instance, when it's multiplied by negativity, then of course this becomes blue, red, and this becomes blue, and so on. It will flip as it's multiplied by this time course. Okay, I think I won't go through this gradient descent approach to maximizing the joint information, the joint entropy of the two components. So Infomax is the approach that we learned from Tony Bell. It can also be derived as maximum likelihood that the components it's finding are actually independent. But I'll leave that to those more mathematically inclined. So ICA was hinted at in a paper in '86 by two French mathematical engineers. Bell and Sinofsky's paper that I read was about Infobac's ICA approach, was '95. Amari, important theoretical contributions. He's a very abstract mathematician in information geometry, and he talked about the importance of natural gradient learning that made the algorithm more efficient. Cardoso came up with a different approach, joint diagonalization, and Hovaranin came up with his self-named fast ICA, which is not necessarily fast if you want to do a complete decomposition, and is not as accurate as some other decompositions, as we'll see. The extension of Infomax ICA to deal with what's called sub-Gaussian sources was produced by Taewon Lee and Mark Girolami here. And we used that originally until Jason Palmer came up with a generalized version of all this, Amico, which is the most powerful, to our knowledge, is the most powerful algorithm for source separation of EEG. So in '96, our '95 paper was published. 2 years later, Martin McEwen in Terry's lab worked with us to apply ICA to fMRI, where it's still used quite a bit today. And Cardoso, with his JADE, showed that you could separate the heartbeats of the fetus from the mother if you record data from the abdomen. A student working with me showed you can also apply ICA fruitfully to ECOG data. Now, important recent result, this is a paper, first author, Arnaud. It showed this, basically. Those linear decompositions of multi-channel EEG data that find components whose time courses are more temporally independent. So the more the ICA is successful, it takes your channels, which are, of course, highly redundant, because they all receive contributions from the same sources. The more it transforms those into components whose time courses are mutually independent, the more of the components are associated with scalp maps that are dipolar. That is to say, can represent and undoubtedly do represent I would say, the projection of a single cortical source. So the more independent the time courses of the components, the larger number of interpretable, localizable, and of course distinct, both numerically and functionally distinct brain processes and non-brain processes ICA has found in the data. So here was the key result in the paper. We took here are 18 algorithms to do linear decomposition, starting with PCA down in the left corner. Jason Palmer gave us a measure of how much mutual information was squeezed out of 70-channel data by the ICA transformation. Very nice measure. There's a function for it. PCA squeezed out almost all of the mutual information because it squeezed out all the correlations. PCA components are all uncorrelated. So there's 41.8 kilobits per second was squeezed out. Through all the algorithms, the best one, which was Jason's Amica, squeezed out 43 points, so only a few percent more. So it's like you wrung out the water in something, and then you tried really hard and you got a few more drops out. But there was a very large change in the results, and that was that the number of interpretable components was now much larger, much larger. Where PCH produces after first few components that lump together different sources, it produces sort of checkerboards. It has to. It can't be associated with any source, any physiological source. So luckily, we'd started here, and so we don't have a reason to change our approach. Although the results of these other algorithms are not incompatible with ICA. They're just not as fruitful as incompatible with Amica. So the more independent the time courses, the larger number of interpretable and functionally independent components, processes you isolate. So I'm going to talk about the assumptions of ICA. It's important. Mixing is linear at the electrodes. Well, that's true, biophysics, simple biophysics. If there were gigahertz, maybe there would be some, non-linearity, but there's not. Propagation delays are negligible. Again, yes. Component locations are fixed. Well, that bears some thinking, right? Because I talked about sleep spindles in which they don't seem to be fixed. Component type courses are independent. Well, again, one can say, well, why should they be independent? And then if you're only getting the number of components that you have scalp channels, is that enough? Well, that's also bears on thinking about. And here's a picture for something, a schematic picture for that. Let's say you sorted all the effective sources of EEG by amplitude from left to right. Well, you have, this, out here or out there might be individual synapses, individual, et cetera. That tail would go on forever, although, of course, unresolvably. So if you only have this number of channels, then you have to, then ICA could only find that many sources. And that means also that all this other volume of activity has to be folded in and mixed into the sources you get. So it's better to have more channels, for sure, within some practical limit. So the only question is then how much of that gets folded back in? And our heuristic, we don't have ground truth, but our heuristic evidence is that the dozen or so processes that we typically, brain processes that we actually extract from EEG data sets, really account for some large fraction of the variance in the EEG that's not accounted for specifically by eye blinks and muscle, things we can recognize as non-brain or artifact processes. So that there's relatively few, the EEG is dominated by relatively few of these effective source processes. Now, should they be independent of each other? Well, physiologically, here's the rationale. These are, let's call those the pyramidal cells, and let's call those excitatory cells, and let's think of these as the inhibitory cells, interneurons. And their tight interconnections mean, and particularly since the inhibitory cells have no long-range processes, so therefore, if they produce spatial synchrony, that should spread through a connected patch, exactly as Walter Freeman first noticed. The connectivity in cortex, lateral connectivity in cortex, is extremely highly weighted toward neighbor contacts, right? It's 1,000,000 times more likely the two neurons will be connected if they're next to each other than if they're a centimeter away, or perhaps even a millimeter. So that means that if this synchrony arises within a patch of cortex, more than one patch of, and also the thalamic cortical columns that sustain oscillations are also very narrow, in the sense that if you take two needle electrodes and put one in the thalamus and move it a little bit, you don't get coherent activity. That coherence is only when they're exactly lined up in some sense. Those two facts alone mean that activity should spread through these emergent islands of relative synchrony in independent ways. There's no strong connections to keep them going. And so the idea that these represent independent domains of local synchrony is physiologically very plausible. And of course, they should be, their sign is that their scalp map, their scalp projection, should resemble that of a tiny equivalent dipole, a tiny oriented battery somewhere in the middle of the patch or near the middle of the patch. Now, of course, some cortical regions are connected bidirectionally by white matter tracks, and so you could have something like resonant activity that was synchronized across corpus callosum or other densely coupled distant areas. And in that case, you'd expect the dual dipole model would fit very well, the projection to the scalp. And that, of course, is just what we saw. Now, are the locations fixed? In what sense are they fixed? And are they fixed? Do they replicate across subjects? Okay, here's an experiment. Now, what is this? This is the dipole density function that you find in the miscellaneous functions folder. And what we do is replace each dipole with a ball, a Gaussian ball. So this represents the probability across 20 or 30 subjects of finding a component whose equivalent dipole fits to that spot. Okay, so now we see hotspots. For this letter memory task, we see a hotspot in the interior cingulate cortex. We see two hotspots about hand somatic motor cortex. So that means across subjects we find a hotspot there. That means that there is replicability across subjects, even if not perfectly. We see alpha sources, strong alpha sources in the back of the head. Not just producing alpha, of course, but with a strong alpha peak in their spectrum. But here's another experiment. Eyes closed, imagining different emotions, situations that associated with emotion, which might be, like tiger approaching me, I'm afraid. Still, so you get a lot of alpha, of course, sources, but there's no anterior cingulate. There's no distinct signal coming from anterior cingulate across this group of subjects. There is, however, in some subjects, sources in inferior frontal cortex, which would be associated with limbic system and motion cognition. So in different experiments, there's different sources do change. So if you change your thinking in a certain sense, or your experience, the places that these affective sources of EEG pop up do differ. Here is an oddball with a novelty, beep, beep, boop, beep, beep. And and what you see is a source that actually is right in the vertex, so like a dunce cap, if you made a model of it. But that didn't occur in the other experiments. Here is, now, this is the last example. This is subjects who participated in two experiments, A and B, and they did A, B, A, B, A, right, 10 minutes each or something. And so we took all the A's and we decomposed that separately from all the B's. So this is where dipoles ended up in the old new word memory task. Did you see this word before? And you see anterior cingulate, strongly represented, although the diffuse probability across other parts of the brain too. But in the interleaved 10 minutes where they were doing this another task where they show a picture of a hand pointed at an arrow, that means press this button with this finger. So it's just a simple interpret the visual and press the appropriate button. We had a very different distribution, probabilistic distribution of where these independent components end up. So yes, there can be non-stationarity in where the sources pop up, and is there therefore non-stationary ICA? Yes, there is, and I don't have time to go into it, but we can talk about it later. Are they fixed across participants? Well, we saw that. I mean, the co-registration here is rather simple. Of each subject's electrode positions to the head, so it's not extremely accurate. And yet, the size of these dots show that this is the level that we can attain replication across subjects. Those size of those dots are about the extent of the blur that we gave to each dipole position. So yes, there's very specific spatial information in EEG data, even interpreted by with fairly careful but not exact co-registration with a head model. And not only these didn't all have 256 channels also. Some of these had 70 or 128 or even 32. So there's a great deal of spatial information in your multi-channel EEG data that has typically been ignored in the analysis. Arno wants me to finish, so although I'm going faster now, I got the coffee. I had some very interesting things to say. Okay. They'll be in the slides, which I'll give to Arno as soon as this talk is over. Okay, so what are the properties of independent components that make them so useful for source-resolved EEG brain imaging? They're maximally temporally independent. That's how they're defined mathematically. So in a sense, they do different things, but they're concurrently active typically. And they can be separated from each other in a way that no other filtering can do. They have highly overlapping scalp maps, so they give you much more spatial information than is available in the scalp data itself. They have similar power spectra. Well, I don't know what I meant by that. They have a and that slipped in somehow. They actually have very individual power spectrum, although of course all on the 1/f baseline, which is characteristic of cortex. And many of them have dipolar scalp maps. That means they're compatible with origin in a single cortical area. Occasionally in two symmetrically located cortical areas. It turns out one of our visiting scientists discovered that that's not true at 6 months of age. There's many more of those at 6 months of age than there is at even 12 months or in adults. So one can learn a lot, I believe, from doing this analysis. But then for cognitive neuroscientists, these temporally independent, distinct activity profiles turn out to have distinct correlates with behavior and conditions and experience. So they're functionally distinct, and that's the real reason. Rather than getting a mixture, a smushing together of processes with various functional associations, you can find processes with very distinct associations. And I didn't have time to show you the ERP paper that we did, Rissling et al., which took a mismatch negativity, standard auditory paradigm, and decomposed it, data from schizophrenics and non-schizophrenics, collected here at UCSD, and decomposed it by ICA, and found a network of 6 frontal, temporal, and parietal sources that contributed to this mismatch negativity. waveform. And then when we looked at just the simple amplitudes and latencies of peaks and ERPs at the source level, rather than at the channel level, we found distinct, in those different clusters of sources, we found distinct relation and strong relationships statistically with positive symptom scores, negative symptom scores, ability to care for oneself, working memory, visual attention, et cetera, et cetera. So for the first time in the career of the investigator, he found we can now find, we can do single subject, we can characterize single subject differences using the simple EEG test, which was never possible with a scalp channel. Why? Because it mixed together everything. So I'll finish just with a remark here about PCA. Some people get confused. Is PCA the same? I don't know, holding up the stop sign. So, okay, Arno did this, so. Here's a data set. Think of it as a 2-channel EEG data set, but of course it doesn't matter if it's EEG or whatever. And look at the left panel there. And the left panel shows what PCA will, so the vertical axis is channel 2 and the horizontal axis is channel 1. So you just do a scatter plot of time points. And if you give it to PCA uses Gaussian glasses. It sees everything as a Gaussian cloud. So seeing it as a Gaussian cloud, it finds those two axes. The number 1 is the principal axis. That's where the most projected variance is. And number 2 is orthogonal to that, and says that's my Gaussian cloud. Well, unfortunately, the data is not a Gaussian cloud. So on the right, we see what ICA will do with the same pattern. And what we see is that it finds the two axes of independent covariation, or independent variation in the data. It says, if this data is produced by two variables that add up, then these are the two variables. So it identifies how each one of those projects to the two channels, with what proportion in this case, a simple scalp map, two-dimensional scalp map. So that's PCA lumps together as much variance as possible in each successive component. So PCA lumps, ICA splits into separate information sources. Okay, so they're both linear decompositions, but they have completely different goals and therefore different results. And okay, so now I'll end with this slide. This is a cautionary slide. Arno had there's a plugin I hope still available for EG Lab that'll send a component scalp map to Loretta, low resolution electrical tomography analysis, I guess. It's widely used, and what it does is exactly what it says. It does low resolution sort of probabilistic source analysis. So there's the component process that we gave it, and then this is the low resolution solution. Problem is that people are using these packages, and I'm afraid it includes EG Lab too, and just presenting the results as this is the source. Sometimes without even the method being announced, yet alone discussed all the assumptions of that method. So I'm thinking of writing a paper, saying this is not good, right? Because this is not where the source is. It doesn't occur diffusely over all that part of cortex. That's physiologically highly implausible. That doesn't mean the method is wrong. According to the assumptions of the method, that's the best solution. Okay, so be aware of that and particularly if you just try to take some peek in your scalp ERP and you find some solution, it's like this. Be aware that doesn't mean your ERP comes from that all this territory and all that proportions. What we're trying to do with ICA is to find the exact patches of cortex where the source resolved EG principally comes from, and then find their exact functional significance. And ICA is a wonderful tool for doing that, but it doesn't solve the whole inverse problem. What it does, it tells you what processes are contributing to your scalp data. to find out where they are coming from, if that's your goal, you have to use these inverse methods, and the inverse methods are of different simplicity, different qualities, and make different assumptions. Okay? There's a lot more to say.